So the marginal distribution for x, well, x is 1 at this point here only, so there's a probability of a quarter. X can be 2 if we get either of these points, so there's a probability marginally for x equals 2 of a half, and there's a probability of a quarter there. Similarly, the marginal distribution for y, there's a probability of a half at 1 for those 2 points, and for these 2 points there's a probability of a half at 2. The conditional distribution of x, given that y equals 1. Let's fix y to be 1. The point has to have come out to be one of these two here, and we're interested in x, so x can either be 1 or 2. You can get the conditional distribution by taking the joint and dividing by the marginal. So it's a quarter divided by a half, which becomes a half. But the best way to think about it is this. If I fix y to be 1, x has to be 1 or 2. The original joint probabilities were equal, so x will be equally likely to be 1 or 2, so the probabilities have to rescale to be 1/2. And I'll just write this in here in blue. So this is the conditional distribution. It's conditional of x given that y is equal to 1, and it has a probability of a half there and a half there. And the same thing happens up here for the conditional distribution. If we fix y to be 2, x has to be 2 or 3, and it takes those values with equal probabilities. So that gives us both of the marginal distributions and the two conditional distributions. Let's think now about eta of y. That's just the mean of each of the conditional distributions. So if we think about fixing y to be 1, eta of 1 is just defined to be the expected value of x given that y is equal to 1. It's the mean of this blue conditional distribution. Half the time it's 1, half the time it's 2, so this mean is clearly 1.5. And equally, eta of 2 is the expected value of the conditional distribution of x when y is set to be 2. Half the time it's 2, half the time it's 3, so it has a mean of 2.5. And let's just think about what x is. Down here, the marginal distribution for x is symmetric around 2. So we can see immediately, I'll just put a little triangle there for the mean of x. That's the balance point of this probability mass function. The mean is clearly 2. The main intuitive message I want to get across here is that you can think of the mean of x as being 2 as being a weighted average of the conditional means for different values of y, weighted by the probabilities of those. So in other words, when y is 1, which happens half the time, x averages 1.5. And when y is 2, which happens half the time, x averages 2.5. And so it'll average, its overall mean will be the weighted average of those. So what I'm really saying is that the expected value of x can be written as the expected value of x given that y is equal to 1 times the probability that y is equal to 1 plus the expected value of x given that y is equal to 2 times the probability that y is equal to 2. And you may recognize this as being very similar to the law of total probability, but in fact it's really just an application of our overall formula. The expected value of x is equal to the expected value of the expected value of x given y in this case. So what I'd like you to do now is just to think about what this random variable is in this case, the expected value of x given y. What is it? And I want you to write down its probability mass function, the probability mass function of that random variable. Okay, this might look a little strange, but if I've got a random variable x, it has probability mass function p sub x. This thing here is a random variable, so it has probability mass function, which is written like this. Write those two things down and we'll reproduce this argument using the formula here.